So to recap, where we are now in philosophy of science is, well, we follow a couple of steps that largely Western society took following a movement, a philosophical movement we might call idealism. In idealism, you can kind of conjecture about the way things ultimately are, maybe the notions that are leading us towards some kind of primary absolute ideal, or that are leading society or even nature itself towards some kind of ultimate truth or factual reality, or as Hegel called it, spirit, right? Ultimate absolute ideal spirit. Well, then we talked about the movement that stressed the notion of empiricism, the notion that, well, a response to idealism, which points out that I can come up with almost any kind of idea and then say make it make sense, right? I can try to come up with some sort of internal logic that gives it some level of credence, right? But I can do that with almost anything, right? Many religions, for example, or many sort of theories are just kind of imagined, but without much confirmation. So we talked about, and when we in the discussion about empiricism, we talked about how the Vienna Circle and other philosophers were trying to come up with ways for insisting that an idea that you might have requires some level of verification, or something that we can observe about nature that can confirm whether this idea is in fact true, or according to the way that the logical positivists would say, meaningful. Right? They thought that statements are only meaningful if they can be observationally verified. Well, we saw some challenges with that, right? So we can notice that I can come up with some sort of theory and then actually come up with some sort of verification for it, but that might still not necessarily get us there in terms of a confirmation that the theory is accurate. Let me give you an example. Actually, I'll use this example when we move forward to this new week's content when we talk about falsification. Here's an example. My theory might be the Earth is flat, right? So that's a theory I have, and as the logical positivists would insist, I need observations to make that theory, first of all, meaningful, and second of all, credible. So, all right, well, look around us. We certainly don't see very much curvature in what's around us. It looks like what's around us is a big disk, right? Okay, so that might be an observation that seems to work towards, or seems to provide some evidence towards, the idea that the Earth is flat. All right. So, and you can just point to all sorts of different kind of evidence. You just this huge mountain of evidence. Consider, all of and it's hard to tell how serious people are being when they defend the idea of a flat Earth. But it does seem as though there are some people who genuinely believe that the Earth is flat, right? And perhaps for some of the reasons that I might have mentioned, right? These sort of observational reasons that the Earth seems to be flat when we just simply look at it, right? Okay, well, along come some other thinkers, especially somebody that the text ensures that we think about, named Karl Popper, who said, "Now, hang on a second. Yeah, verification and confirmation doesn't necessarily get us there, because we can still come up with some sort of theory and then come up with all sorts of different ways to verify it, but it might actually not be true in the end, right?" So Popper insisted that a viable scientific theory is one that actually contains conditions of falsification. There should any theory worth its weight in salt should come along with a qualification that says, all right, if this theory is false, then here's what we should observe. Right? There should be ways in which we could corroborate the theory and then possibly refute the theory, right? Now, that may seem a little bit paradoxical, because you might say, well, shouldn't all theories that are true not be falsifiable? Well, Popper said, yeah, but there needs to be these conditions that enable us to confirm through falsification that whether the theory is true. Think about it this way. So here's a condition of falsification for the theory that the Earth is flat. If the Earth is flat, then we should observe certain kinds of things, for example, about gravity, right? So one of the things we know about gravity is that gravity pulls things towards some kind of center of mass. Gravity is like an aggregate force such that whenever there is an object, any object will pull things towards its center of mass, right? Basically the center point of all of its contents, right? Well, if the Earth were flat, that means the center of mass would be around the center of that sort of generally disc-shaped object. Well, if that were true, well then, gravity would not go directly down. Gravity would go towards the center of that flat Earth. And in many models of the flat Earth, that is what the Arctic is at the center. So everything would be my gravitational pull that I experience would always kind of pull me a little bit north, not really down, not so much down, but pull me a little bit more north. I should be continuously sort of leaning in a way that offsets the northward pull of gravity, right? So that would be a condition of falsification. If the theory is true, then this is what we should observe. But we don't observe that. We actually don't observe a net force pulling us towards the north, right? Or towards the center of the Earth, wherever it is, assuming the Earth is a disk. We don't see that. So Popper insisted that this means that the theory that the Earth is flat can only really be a viable scientific theory if there are conditions of falsification. Here's an example of a condition of falsification. Here's what we should observe if the Earth is flat. And then we might say, well, do we observe it? Okay, well then if we do observe this like gravitational pull towards the north, then that contributes to the validation of the theory or contributes to the verification of the theory. Still doesn't totally prove the theory, right? Because remember, there's another important detail about the chapter that we're talking about now. When we're dealing with an accumulation of evidence, we actually never quite reach a point where we have sufficient evidence to be 100% certain. We never actually reach that point with a careful scientific process. Now, we could say that we very, very strongly, we have very, very strong and plentiful and logical evidence for something, but there's usually some remote, perhaps unlikely possibility that we've been mistaken, right? In all of these many observations, right? That's always a possibility. So it's very, very rare that you'll see a scientist say, we have proven this, right? Science is not really about proving. It is about presenting a lot of evidence and also with the possibility that things could be falsified. And if it's false, here's what we should observe. Now, of course, let's say we do observe something that falsifies a theory. Is that the end of the theory? Not necessarily. We may revise the theory. We might say, actually, well, then we need to correct things here. Let me give you an example of this. One of the things that Charles Darwin hypothesized that when he kind of came up with this theory of the origin of species and how natural selection seems to work and how species seem to kind of grow and mutate over time over many generations, and that nature basically determines which ones will end up surviving and reproducing because of the conditions that animals live in. Okay, well, Darwin thought that if this theory is true, then we should see lots of fossils around that show like these transitional species, and we should see a very smooth pathway from one one sort of species towards its descendants, right, toward its progeny. Again, over many generations, we should see a smooth fossil record, but we don't see that. Right? So now there are transitional fossils, but we don't have that smooth timeline of fossils over time that Darwin anticipated would be the case. So he provided a sort of condition for falsification for his theory, and it turns out that we sure enough we don't see those transitional the smoothness of the transitional fossils. But we do see transitional fossils. So what we've needed to do is we've needed to add some revision to the theory. And actually, as it turns out, Darwin's understanding of how fossilization occurs needed to be updated. It turns out that fossils are actually very rare. It's hard to come by a fossil. There need to be certain ideal conditions around the death of an animal or a plant or something living. There need to be certain conditions around that death in order for the remains of that creature to be preserved over thousands, millions of years, really. So fossilization itself is very rare. And that helps to explain why the initial conditions of falsification that Darwin provided actually don't really falsify the larger theory of evolution, um, because we needed some more understanding about how falsification occurs. Okay, so I hope this is a helpful kind of overview of this additional kind of module that we add onto our understanding of the scientific process. That there we can confirm things, but really a viable scientific theory will contain conditions of falsification. I should be able to make some observations that will determine whether the theory is actually true or actually false. Okay. All right. So I've given a couple of examples of how falsification can be used. And remember that Karl Popper, the one of the one of the terms that he used to describe this is he thought that conditions of falsification are a very helpful way of distinguishing actual science, like valid science, from pseudoscience, right? So I hope that's helpful as a condition of demarcation, as Popper called it. All right. So what I'd like for you to do in your discussions for this week, I'd like for you to come up with some kind of like theory about nature, right? It could be any sort of wild theory, or I don't know, maybe say a theory. Oh, here's a sort of conspiracy theory that that birds, or that there are birds that have detection mechanisms, and that enable that some government or some large corporation to spy on us or something like that, right? So it could be something like that, right? Some sort of theory about something related to nature, or it could be a theory that. Well, let me give you an example of something that we had come up with between my wife and me. There was a time when I thought that you didn't necessarily need to like rinse out a sponge. I mean, I didn't want to like after using it with soap. I thought, well, it's kind of a waste of soap to like squeeze out all the remaining soap that you didn't use and just put it down the drain. Why don't you keep the soap in the sponge, and that way next time you're going to clean something, the soap is there and it's not been wasted. You know, I'm a little bit kind of frugal like that. Well, my wife said, well, no, actually, if you just leave it there with the soap in it, it's actually going to get it's going to start to grow mildew, right? And it's going to start to smell after a while. Bacteria will grow in that sponge. And I thought, well, no, but there's soap in it, right? And actually, the soap is antibacterial soap. So the bacteria is not going to grow in the sponge with the soap there and then start to stink because there's antibacterial soap in there. Okay, well, this was a hypothesis. It was sort of like a theory. Hypothesis and theory are very similar ideas, just like an educated guess based on observations. What are my observations? Well, antibacterial soap is good at killing bacteria, we might say. Um, all right, so then what happened? Well, I went ahead and let a sponge sit for, gosh, a couple days. And sure enough, it started to give off a little bit of an odor. My wife was right. Now, notice, so my hypothesis, if my hypothesis were true, then we would not detect an odor in the sponge after a couple days. However, we did detect an odor in the sponge in the other side. So my hypothesis is false. Right? Now, you might remember last week's video had to do with logic, and you noticed that the syllogism, or the rule of inference that I just used in that argument is modus tollens, right? If we observe this, then this would be the case, but we don't observe this. I'm sorry, but then this would be the case, but it's not the case, and so. Well, no, let me put it this way. If my hypothesis is true, then we should observe x, right? We don't observe x, therefore my hypothesis is not true, right? Modus tollens going that direction, right? Anyway, we're going to go in a little bit more detail about the logic for that. Or just to put it another way, yeah, if my we know my hypothesis is not true, because if it were, then we'd see this, right? But we don't, so it's not true. Okay, that's an example, just another example. So come up with your own theory of nature, and it could be silly. That's fine. And then think about like what you have seen that have led you to believe that, right? So what sorts of things about nature might prompt that kind of conjecture, right? That kind of hypothesis. Then think about what else you would observe if the hypothesis is true. What else would we see? How could you sort of test this, right? And think about what you might observe if it's false, right? Are there conditions of falsification? What might you observe if it's false? Okay? Have fun. I look forward to you watching your responses.